Now, continuing B in this exercise with the AB condition, we will now show that if A and B lie inside this area here, so the last area we're looking at now is the one where A is greater than 1 and where A plus B is greater than 0. And then we want to show that QK does not define a probability distribution. Intuitively, we can kind of already guess that what we want to do is to show that the sum of probabilities will be equal to infinity. And that cannot define a probability distribution because the sum of point probabilities must be equal to 1 in a probability distribution. The reason why we can kind of guess this without calculations is because if you let A be greater than 1, then and you let B be given such that A plus B is greater than 0, then more or less this term will let the QKs be growing, right? You can kind of imagine at least that on this quadrant, the QKs will just be strictly growing all the time. And as soon as that happens, we know that we can in no way make the QK sum to something finite. So that's kind of the intuition. In order to calculate this formally, let's try to write QK in terms of A plus B and not just A plus B over K, because we have some assumptions on A plus B and we really want to use them. So the way we can do that is, well, I have A plus B divided by K, and well, I would really like to have something where it's just A plus B. So the thing that I'll do is I have A plus A divided by K plus B divided by K minus A divided by K. So I just add and subtract the same thing. And the way this is going to help me is then I have a term where I just have A plus B. And I can say this term is greater than 0, right? And then I have another term where I have A multiplied by 1 minus 1 divided by K. And I can actually in some way say that this term is more or less greater than 1 if K becomes big enough. So if we go far enough into the tail, this entire thing will become bigger than 1. And far enough into the tail, the things will just increase more and more and more. Well, I could almost just finish the argument here, but we can also do it a bit more formally as well. So let's see what we have. We have A plus B multiplied by QK minus 1 divided by K plus A multiplied by K minus 1 divided by K multiplied by QK minus 1. And we know that this is greater than equal to 0. We know that this is greater than equal to 0. We know that this is greater than equal to 0. So this entire term is greater than equal to 0. And then we have that everything is greater than equal to A multiplied by K minus 1 over K QK minus 1. Now, since A is greater than 1, we can remove the A and pay for that by another greater than equal as such. And let's just try to look at what this is. Well, QK minus 1 satisfies the same relation as QK does. So this is actually, in fact, greater than equal to K minus 1 over K, and then K minus 2 over K minus 1, QK minus 2. But I could just carry on and say that's greater than equal to K minus 3 over K minus 2, and then QK minus 3. And I can go on and on and on and on and on and on and on until I have K minus K plus 1, and then I have a 2 here, and Q1. So I just push this all the way down until Q1, and then see how everything cancels more or less. So This is equal to Q1 divided by K. And this is nice because now I have found a lower bound for QK in terms of K. And this means that if I want to sum my QKs, at least for K equal to, let's see, for K equal to 1 up to infinity. So I do not have the 0 with me, but that's okay, because if this is greater than infinity, then with the Q0 term, it will also be greater than infinity. So this is greater than equal to Q1 divided by K, and I can just move out the Q1 here. And then I have 1 over K equal to 1 to infinity. And from analysis 1 or 0 or something, we know that this sum is infinite. So this is equal to infinity. And therefore, QK is not a distribution, a probability distribution. Or we can also say it doesn't specify the point probabilities of a probability distribution. So that was B, and now we have in B established that in order for the AB condition, here to define the distribution function, you must have A's and B's inside either this region, or this region. And in the next exercise, we will show that if A and B lie inside one of these three regions, then the probability distribution that results must necessarily be either binomial, Poisson, or negatively binomial.